So welcome everybody, third day of the GIAN short course, Elements of Smart Structures. Professor Chauhan told me that I should announce that we have a special dinner this evening at the guest house at 8 p.m. I think first floor. I'm not sure if you got the announcement, but he asked me to say it before the first lecture. So in this lecture, we will are back again at piezoceramics and have a look at, let's say, the manufacturing way from piezoceramics to piezocomposites to functional modules we then use as piezoelectric transducers like the ones here applied on the CFRP beams. So as mentioned, we are on the third day, first lecture. Later on, after tea break, we will have lecture on actuator stroke amplification, and then the third lecture, structural integration of functional modules with a short introduction to composite structures, and then in the afternoon after tea we have the third lab. So we are starting with a short introduction in piezoceramics, semi-finished products, piezocomposites, and then we have a look at functional modules. Like in the other lectures, learning goals. First learning goal is that you are familiar with various piezoceramics semi-finished products and that you can describe how they are manufactured. Then you are able to justify why we combine piezoceramic materials with polymers to piezocomposites. And then this combination can be done, these composites, in different ways. And with this, we get different connectivities of piezoceramics with the polymers. And for this, you can also give examples. Second last learning goal, you are familiar with different designs of functional modules. So the end product for this lecture. And you can also explain the manufacturing process of these functional modules or transducers and explain why we have compressive residual stresses in the ceramic and why we want to have them. So again, an overview about the different materials. Yesterday we had a look at piezoelectric polymers, for example, PVDF, or the dielectric electroactive polymers and the ionic electroactive polymers, and to use it as a multifunctional material which also has load-bearing properties. We can see that here the Young's modulus of these materials is quite low, and also the blocking stresses are quite low. So we'd like to use the piezoceramics in combination with, for example, CFRP or aluminium to really use the multifunctionality of these materials. Piezoceramic semi-finished products for surface actuators for these functional modules can come in plates or thin films or discs, so rectangular plates, circular plates, or annular plates, like shown here, different shapes of these thin plates, and freeform shapes, like for example these ones, are also possible. We can just cut them by laser with water jet cutting, or also have additive manufacturing processes to manufacture these piezoceramics. At the moment we have a former PhD student at our institute who founded a company who will additively manufacture piezoceramic materials, so you can 3D shape these transducers. Typical thicknesses are between 100 and 500 micrometers, so between 0.1 and 0.5 millimeters, which is also in the range of a single ply of a composite material. And typical dimensions for these rectangular plates like these are 50 by 30 millimeters. But there are also special sizes up to 100 50 millimeters edge length. And this is also, so 50 by 30 is also roughly the size we have in this transducer, which is applied on the CFRP beam. Another form of piezoceramic semi-finished products for surface actuators are fibers. We can have round fibers or hollow fibers or strips. Round fibers with diameters between 30 and 800 micrometers up to 200 millimeters in length. Yeah, the other cross shapes here are similar in dimensions, so also up to 800 micrometers with an inner diameter between 200 and 400, or strips or rectangular fibers, again up to 800 micrometers. And you can see here these fibers with an €1 coin as a comparison. One manufacturing process is dry pressing, as in incoming parts or products. You have these lead oxide, titanium oxide, zirconium dioxide, and some doping elements, for example. Then you blend them, homogenize and mill them in an aqueous medium. Then there is a calcination process at 900 degrees Celsius to get rid of some byproducts you don't want to have in the blend. And then you mill it again to enhance the homogeneity. And then with this powder, you go in a press process, or you press them in a die with some adhesive additives, and then dry this and shape this. And after these process steps, you have the so-called green body of the piezoceramic. And this green body then goes into a sintering process where you grow the grains, so the grains get larger and not really structural, or you don't have really structural integrity in this green body. It's just a compressed powder, and with the sintering process you increase the mechanical performance. It's performed between 1100 and 1300 degrees Celsius. Then we need, of course, the metal coating to apply the electrodes, to be able to apply the electric field if we want to use it as actuator or sensor. And afterwards the polarization we spoke about yesterday to macroscopically use the piezoceramic effect. So same process, or process starting from here, so not the material preparation but the manufacturing of the semi-finished product. You have the ceramic powder in a mold, then compress it. So afterwards you have the green body. The green body goes into the sintering process, 1000 between 1000 and 1300 degrees Celsius. And then you, for example, can cut these thin plates from the green body and have the plates you can then further use for building these transducers. And here you can see the grains after the sintering process, for example. There's a second manufacturing process called slip casting. The material preparation is basically the same. Then you blend it with the wet material, solvents, adhesives, and also plasticators. You evacuate these material then, and then you have a strip casting where you scrape it with a spreading knife, dry it afterwards to evaporate the solvents, and then you cut it to shape. Again, have a sintering process, and then like before, the metal coating for the electrodes and the polarization to get the macroscopic properties. this looks like this. You have the slip with the ceramic powder, binders, and solvents. You have it in these kind of street box, and pull it then in this direction on a belt. Here it is dried. Here you have then after drying you have the green foil comparable to the green body before. And afterwards you cut it to size and then go through a sintering oven and or furnace and have the unpolarized ceramic material afterwards. These two manufacturing processes are for the plates or for the thin films. We also have these piezoceramic fibers we already spoke about, and the manufacturing process for these fibers can be similar to the slip casting. So you can also have an extrusion from a slip comparable to the slip casting, but you can also use wet spinning. Then the ceramic powder is in a cellulose solution and forced through a spinneret, and it passes then through a chemical bath in which the cellulose is precipitated again. So you get rid of the cellulose, you only need it for the process. And the third process would be Sol-Gel spinning. You have a metal organic compound and also solvents and a suspension. And then at first you have the small ceramic particles in this mixture. It's called the sol, and then this is forced through the spinneret again, and it forms to a gel to form the fibers. So therefore it's a sol-gel process. And these piezoceramic fibers then are again the green fibers, which are elongated and sintered. And the size of the sintering furnace determines the maximum length of the fibers you can get from it. Yeah. Yeah, it just means it's the material before sintering. So after it's the pressed powder which is dried, but you don't have sintered it yet to get structural integrity of the material and to grow the grains and have really a stable material, so to say. So it's just an intermediate form of the material during manufacturing. So we are now done with our piezoceramic manufacturing. We have piezoceramic plates or foils or the fibers, and we are now coming to the piezocomposites. Why do we may build up a composite and not just use the piezoceramic material? The piezoceramic has several advantages: a wide frequency range for dynamic application. We have a high stiffness, up to 60 or 64 gigapascals. We have a simple actuation by the electric field. It can be manufactured in an industrial scale, and it's good, has a good availability and also reproducible quality. But there are some disadvantages. We have a low active strain, only 0.1%. It's highly susceptible to fracture. It's a very brittle material, the ceramic. And depending on the ceramic thickness, you need high electric voltages to produce the electric field to actuate them. And therefore you need a reliable electrical insulation and also a reliable contacting of the electrodes. And to make the piezoceramic really usable for our applications, we improved the properties through the combination of the piezoceramics with the polymer. And then we have a piezoceramic polymer composite, for example, by casting, bonding, or laminating. The properties enhanced by combining these ceramics with the ductile polymer material. So we have the brittle ceramics with the ductile polymer. the piezocomposite consists at least of 2 different materials, which we will have a look on later on, because these 2 materials during the manufacturing process form residual stresses, which are pretty useful for the piezoceramic. And therefore we also get entirely new material properties compared to the individual materials, the ceramic and the polymer. And what plays an essential role is the arrangement of the phases, the piezoceramic and the polymer relative to each other. So we have an overview again. We first spoke about the piezoceramics as films or fibers, how to manufacture them. And now we're going to have a look at the packaging to build really the surface actuator, the functional module, where we need mechanical stabilization, the insulation, electroding, and also the electrical connections. And then we can just apply them or integrate them into the material. And structural integration is the topic of the last lecture today in fiber composite materials. So what are the advantages if we build piezoceramic surface actuators as a composite? We protect the brittle piezoceramics against external loads. We have really defined mechanical and electrical boundary conditions. Again, the compressive residual stresses we will have a look on later. We inhibit crack propagation in the brittle ceramic. With this, we increase also service life of the actuator or the transducer. We don't need a massive load introduction. We can just bond the functional module, for example, on the structure to apply it. We only need small installation spaces, and with this we can also use it in thin-walled, lightweight structures. And we can also integrate it in CFRP or GFRP structures, so really in the load path. These are some examples for encapsulated piezoceramic fibers and foils into a transducer. We have transducers made from foils, like this one from German Aerospace Center. We have transducers made from foils with different type of electrodes, an interdigital electrode. Here we have a planar electrode. And we can also have transducers from rectangular fibers with interdigital electrodes. And we will, in the next slides, go through different types of these transducers or functional modules, and also have a look at the different effects we are using, D33 effect and D31 effect. And I still have a bit of a cold, so my voice is a bit strained. I hope it will make it through the day. I already mentioned the connectivity. The connectivity defines the number of orthogonal directions or dimensions of a face that extends continuously within a composite. So we could have a 0 connectivity, which stands for a particle, like here. We could have a 1 connectivity. This would be an extent in one direction, so fiber. Or we could have a 2 connectivity, which is a foil. And with this, we can describe the connectivity in a piezoceramic composite with MN connectivity, which describes the 2 phases. Phase 1 is the ceramic phase, and phase 2 is the matrix phase. So we can describe with this in which form the ceramic is inside the composite, and in which form the matrix or the polymer. So it's a polymer matrix is inside this 2-phase composite. then we can have a look at what the connectivity means for the overall permittivity. We can have this kind of connectivity. So we have here the piezoceramic, and in yellow we have the matrix or the polymer. And then the question is, for our small signal behavior, how is the overall permittivity of this series connectivity, because it would change sorry, it would change with respect to the if we have only piezoceramic material. And in this case, field in this direction and an applied voltage again, or an external force or pressure, we have just a series connectivity. So Lk stands for the length or the height, length or the height of the piezoceramic material, because in German we write ceramic with a K, therefore we have K on this, and LP is P for polymer. So LP is for the matrix, or everything with index P is the matrix, and everything with index K is the ceramic. And like with springs, we have a series connectivity. So the length Lk divided by the permittivity of the ceramic times the cross section, which is the same for both, A plus Lp divided by the permittivity of the polymer times the cross section. And if we then transform it to epsilon to epsilon 3 C, C then stands for the composite, not for ceramic. Then we have an equation for the overall permittivity of a series connectivity. And we can do the same for parallel connectivity. Now we both have the same length or height. We have again field in the 3 direction and also a force here. But now the cross section is divided in AP for the polymer and AK for the ceramic. And then we have this equation, which is similar to series connectivity of springs again. Permittivity of the ceramic times the cross-section of the ceramic plus permittivity of the polymer times cross-section of the polymer. And then again we can transform it to the permittivity of the whole composite and get again an equation for the total permittivity. Now we can have a look at different connectivities for these two-phase composites. So we have the MN connectivity. We have the ceramic phase as the M connectivity and the matrix phase as N. So 0, 3 would be a particle of ceramic into a volume of matrix, and we can have 0, 0 particles in particles. We could have 1, 1, so ceramic fibers with matrix fibers, or we could have a 2, 2 connectivity where we have a stack of films, so a film of ceramic and then a film of matrix and so on. And common connectivities for piezocomposites in engineering applications are 0, 3, so this one, ceramic particles in a matrix of polymer. 1, 3, where is this here? 1, 3 would be fibers, ceramic fibers in a volume matrix, or 2, 2, which is again the stack of the different films, so film of ceramic material, film of matrix, and so on. Is this clear? I think it's, yeah. So the first one is the ceramic and the second one is the matrix. And if we have in this row 1, we have always fibers of ceramic, and the matrix phase changes also fibers or plate-like or two-dimensional matrix extension, and here it is three-dimensional. So you have matrix elements in every 3 directions, so to say, if you in this model of yeah, finite elements or cubes of material. Does this answer the question? Not really. 1, 3 is given, yeah. How we can draw it? Or? Maybe I don't get the question right. Maybe we go a few slides ahead, and then maybe we talk about it afterwards. Okay. Yeah. So we start with 03 composite particle in a volume of matrix material, piezoelectric particles in thermoplastic or thermoset matrix. The ratio of the components, of course, also determines the transducer properties. The more ceramic we have, the more capable is the transducer afterwards. And with this simple rule of mixture, we can also estimate the density then of the ceramic, which is of interest if we are looking at lightweight applications, which is the overall density is the ceramic volume fraction times the ceramic density plus 1 minus the ceramic volume fraction. So the matrix volume fraction or the polymer volume fraction times the polymer density. And here you can, it's a bit small, but here you can see this real image of the 03 composite with these ceramic particles in it. If we want to build a transducer from the 03 composite, we start with our powder, like shown in the beginning, then mold and cure it and have the sintering process. We have the electrodes applied to it. So this is already the composite material, not just ceramic. Then we polarize the piezocomposite, and then we can use it as a transducer. Our polarization direction is in the direction of the field, but we would use with the surface actuators or transducers the in-plane elongation of the in-plane strain of the transducer of the material. So what effect would this be? Do you know it? Is it D33 or D31 effect? 3-1, yeah. Yes, because the field is in 3 direction and we use the 1 direction for the actuation. And we have electrodes on top of bottom, at the top and at bottom of the composite, so the field is in 3 direction. Then next composite with different connectivity is the 1-3 composite. It consists of piezoelectric fibers or short rods with a thermoplastic or thermoset matrix again, so fibers in a volume. we can manufacture them by embedding the fibers, so have really single fibers and embed them. We could also slit and fill them, so cut through a monolithic block of piezoceramics and build in that way fibers which are then filled with the matrix material. And here we can see a microsection image from a PZT fiber. The scale is, I think, 10 nanometers. I'm not quite sure. I have to enlarge the image. And the ceramic phase is lines, so 1 connectivity, matrix phase 3 connectivity. If we build a transducer from these kind of fibers, we start with round piezoceramic or lead zirconate, lead titanate fibers, then add the polymer, and then we use not planar electrodes, but these kind of interdigital electrodes, which form like this. So you have one electrode and another electrode, which are then called interdigital electrodes. And with this, you can apply a field in this direction, because the field then goes, if we look from this side, the field goes from this electrode to this, from this to this, and same for the bottom. So we have a field more or less in this direction in the middle. And if we look from this side, then we only have for example, the positive electrode. Then we see that the electric field is from top to bottom in the across the cross section of the fiber. So which effect are we using here? Yeah, it's the D33 effect, because the field now is in this direction, and we also use the elongation of the fibers in this direction. So we use the elongation in, elongation and field direction are the same. Here are the fibers, and here is the manufactured transducer where the fibers are in. In the middle, it's maximum. So then here in the middle, it's straight. Yeah, right. So here you mean? Now this is, if we look from this side, so the field is coming towards us, I think, or going into the projection area. Okay, another type of transducer, again 1-3 transducer with a D33 effect, made also from fibers, but now from rectangular fibers. But it's basically the same process. We have the interdigital electrodes, then we can polarize the piezocomposite, have the field in this direction, and also use the in-plane effect, and the transducer would look like this. What could be the benefit of rectangular fibers compared to round fibers? What do you think? Yeah? Less fibers, yeah. I would say it's easier to manufacture, because round fibers have to be fixed during production, otherwise they would roll away, and rectangular fibers stay better in place if you place them next to each other. And also the electrodes have better contact, because you have a line or a surface contact on the fibers and not only a line contact here where it touches only at one line, the electrode. And then we have the 2-2 composite. It consists of piezoelectric disc or foils and thermoplastic or thermoset disc and foils, which are added on top of each other. This is the type of actuator you used yesterday in the lab, stack actuator. And you can manufacture it in two ways, stacking of metallized piezoceramic and connect them alternately. So you have discs with composite discs with electrodes on top of each other, and then you just stack them and bond the plates and solder the tabs at the side, or you stack green foils, so not sintered foils yet, with metal layers, and then sinter the overall stack together with the electrodes and to build up the stack. So this is a 2-2 connectivity with foils of ceramic and foils of matrix interacting, and here you can see also the electrodes in the piezoceramic stack. And each foil is 50 micrometers thick. We can also build use 2-2 composites to build surface transducers. So in this case, with the stack actuator, we use the 3-3 effect because the field and the polarization is in this direction, and we also use the elongation in this direction. And if we use 2-2 composites for surface transducers, then we have the field in thickness direction, but as always for surface transducers, we want to use the in-plane elongation, and therefore here the D31 effect is used. Manufacturing process is the same. We have the composite, the electrodes applied, embedded in a polymer around. So this is already the composite, but we embed it in more polymer for the functional module. We will see later on for the manufacturing of the transducers. So now we are coming to the functional modules. We had a look rather theoretically how they are built up and how the connectivity is and which effect we are using. Now we look at the functional modules, so really the transducers we have on this specimen. And if we compare different designs, we saw that we can have surface actuators with the D31 and the D33 effect. For D31 transducers, we require voltages of around 400 volts peak to peak when they are 200 micrometer thick. But the manufacturing effort is really low for the D31 film actuators because we can use these planar electrodes and don't need interdigital electrodes. But if we compare D31 to D33 actuators, so D31 film actuators to the fiber actuators with the round or rectangular fibers, we see that with the D31 effect, we get less displacement or elongation, only 440 micrometers at 400 volt peak to peak. And for the D33 fibers, we get 1,400 micrometers, so 1.4 millimeters, but we need 300, so 3 kilovolts peak to peak. So these fiber actuators are able to elongate more, but we need a higher factor of volts. So here's factor 2. We need 2 volts per micrometer, and here we need nearly 1 volt per micrometer to elongate them. So the ratio of strain to required voltage is better for the D31 film actuator. So next slide, to compare different designs, fiber actuators with round or rectangular fibers using the D33 effect require higher voltages to establish the needed electrical field. And the spacing of the interdigital electrodes is between 0.8 and 1 millimeter. The manufacturing is very labor intensive because you have to place these fibers manually next to each other before you can embed them in the polymer. And this picture is what I had in mind comparing round and rectangular fibers. I think it's far easier to place rectangular fibers this way to have them in place than round fibers. And you also have large quality variations because it's a manual process, and if the alignment is not perfect, then the performance is also lower. So therefore the process of sawn ceramics has become established, that you cut just the planar foils and have them still connected, and then integrate them. So what do we need additionally to form these transducers? We now have the piezocomposite in different connectivities, but we need more to form the functional modules. We need an encapsulation to have an electric insulation and a mechanical stabilization. We need electric contacting where we can apply our voltage, and we have to connect our electrodes, for example, with a copper mesh. And it's done in a way that we stack non-woven glass fibers, for example, as spacing layers where the cutout is in for the piezocomposites and where the copper meshes are applied to contact the electrodes. Here you have some images of the real materials. Here, this is the copper contact fabric, which is not glass fiber but polyester non-woven material as the filling layers. Here we have the polyester non-woven with the added contact structures cut from the copper fabric, and then the interlayers also made from the polyester non-woven, where you have the cutouts for the piezocomposite material to be placed in. And then the manufacturing steps are that you bond the copper mesh for the contacting onto a prepreg paper, cut or punch out the contact pattern where the two contacts for the voltage are located, then bond the copper mesh and the prepreg paper onto the polyester fleece. This is what we have seen here, polyester non-woven together with the contact mesh. Then we remove the prepreg layer, it's only a carrier, provide the filler layers made of the fiber material with the cutouts for the composites, place the foils inside, and then top it again with the contacting, seal everything, and then we can inject, for example, a thermoset resin and cure it in an autoclave at a, for example, cure temperature of 120 degrees. And after cooling, we cut them to size. This is for 4 transducers in one shot, and then we cut them down to 1. I also have brought a video I'd like to to show. It has German text, so therefore I set it to silent. Here you can see the manufacturing process. This is the piezocomposite, which is then placed in the cutouts. Here's the polyester non-woven. You can see the electrodes and also the cutouts for the contacts. Here are the contacts where you can solder your wires on. Then the electrodes on the top together with the last non-woven ply, some release film, and then a coil plate that you get really planar actuators. And before the ceramic is really brittle, and after curing, you now have the flexibility to bend also the actuator. So this is the final functional module. And here, yeah, you can see the transducers in action. Maybe I jump back to this again, where a plate is actuated and forms like this or deforms like this. One option to inject the resin, you need to fill, let's say, the structure and the non-woven is resin transfer molding, which is also used for composite manufacturing. You have an autoclave, you have here the part with the fibers, so the dry part without the resin yet, and outside you have a resin reservoir. Then you evacuate this part, it's sealed with a foil, and then you can inject the resin, and the autoclave can be heated, and you can also apply pressure and then cure the thermoset material, the plastic, and afterwards you take it out, and then you cut them to size and so on. Now we are coming to the compressive residual stresses in the piezoceramic. The coefficient of thermal expansion of the piezoceramic is lower than that of the structural material or of the polymer, and you have to heat up the whole part for curing, and then you have to cool it down afterwards to room temperature, and it solidifies at around 120 degrees Celsius, and then the layers or the piezocomposite and the polymer around are connected, and further cooling results in greater shrinkage in the structural material than in the piezoceramic. So if you have a look here, we have the polymer here and the polymer here, and the ceramic, or it's more the piezocomposite already in the middle. At high temperature, at 120 degrees or above, then they are connected because the resin cured. And if you then cool it down, theoretically, if you cool it down and they were not connected, the polymer would shrink more than the ceramic material. So you would have a difference here. But since they are connected after curing of the epoxy, or after it solidifies, they cannot have a different strain or elongation because there's strain compatibility, and therefore you have a tensile pre-stress in the structural material and or residual stress. This also should be, and a compressive residual stress in the piezoceramic material. And this compressive residual stress increases the tensile strength of the functional module overall. So this is the reason why you can bend the functional module without breaking it, and the brittle ceramic would just break. Then there are two options or two routes for manufacturing, and the difference is the time of polarization. We could, or factors influencing this compressive residual stresses is, of course, the ratio of coefficients of thermal expansion of the different materials. It's also the ratio of the stiffnesses, and it's the time of polarization. Unfortunately, this is still German, but I will walk you through. We can start with an unpolarized piezoceramic, manufacture the composite, and then polarize it. With this, we have an isotropic behavior because the piezoceramic gets anisotropic after polarization only. Or we could use the already polarized piezoceramic with anisotropic behavior and therefore also anisotropic thermal expansion, and then manufacture the composite. And this results in a reduced residual stress transverse to the polarization direction, and a higher residual stress in polarization direction, and here it's the other way around. We also can have a look at the buildup of the residual stresses. So a simple model again. If we have the different layers, the different individual layers I, the thermal strain forms from the coefficient of thermal expansion of the material times the temperature difference from curing temperature down to, or the temperature where it solidifies down to the room temperature, for example. And this thermal strain would result with the Young's modulus. Young's modulus is not E in our case, but epsilon, would result in this residual stress. And with this we can, or the overall strain would, so this is not the thermal strain, but this is the overall strain. And we can calculate with this equation the stress-induced strain from subtracting the residual strain minus the thermal strain, and then have this in this equation here. And we also have force equilibrium across all layers. So if we sum up the forces of all layers, which is cross-section of the layer times the stress of each individual layer, then overall it should be 0. And we can rewrite this equation from the slide before, the last one with this. So Bi times Hi is the cross-section again, times the modulus times the resulting, or the overall strain, epsilon I, with the equation before. Then we can transform it to this and have an equation for the total strain of the symmetric layup, which is the strain here, the shrinkage between the initial state at high temperature compared to the cured state of the connected layers. And with the different Young's modulus of the polymer and the ceramic, we can then use this residual strain across the different layers to calculate the pre-stress, the residual stress of in the polymer and also in the ceramic. And with this, we can calculate the residual stresses, for example, for different materials. So this and LY556 and the RTM6 are different thermoset materials, which have different curing temperatures, and therefore delta T is different. And here is the insulting layer thickness or insulating layer thickness, and here's the residual stress. And then if we have a look at the different lines, we have here in the middle the stress buildup in the unpolarized ceramics, so same residual stress in all directions. We have about minus 30 megapascals at 0.15 millimeter layer thickness. Here we have, the dashed line is polarization before embedding, and the solid line is polarization after embedding. So the blue line is ceramic polarized after embedding, and this is parallel to the polarization direction. With this, we get the highest residual stress, or the highest amount of residual stress, compared to the green dashed line, which is again parallel to the polarization direction but polarized before embedding. And the same is for the transverse direction. The dashed line is polarized before embedding, and the solid line is polarized after embedding. So with the polarization after the embedding, we get higher residual stresses, which is good for our brittle ceramic material. And if we look at the other thermoset material, RTM6, the residual stresses at the same layer thickness are higher because our delta T is larger. But same overall trends. Sorry? Yeah. We needed to have the ceramic pre-stressed in compression, and if we have a pre-stress or not a pre-stress, a residual stress really in compression, then we can apply more tensile stress until failure. And therefore the brittle ceramic, which would fail under tension earlier than under compression, can be higher stressed under tension, and this leads to a more ductile behavior. This enables that we can bend the actuators to a curved surface where the ceramic without the polymer and without the stresses would just break. Yeah. Yeah, but here is the layer height goes into the calculation of the stress, and therefore the thicker layer would result in higher stresses. Here. Mm-hmm. 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 You mean if the layer thickness affects the maximum elongation of the transducer? Maybe a bit, since this is the structural material which acts against the actuator, but since the polymer has a stiffness of maybe 3 gigapascals compared to the 40 to 60 of the ceramic, I would say that the effect is not large. Yeah. These residual stresses can also be tested experimentally. A simple test is to manufacture asymmetric piezocomposites. So we have at one side the ceramic and sorry, at the other side the polymer, and with different residual stresses in the different layers, we get curvature after cooling it down. And this curvature can be measured, and then from this curvature we can calculate the states residual stress, pre-stress again, but it's really a residual stress, not a pre-stress, because it's not, let's say, an external stress, it's internally. With this, we can calculate the residual stresses inside the layers. So the different materials result in different curvature radius. I'm not sure if the layer thicknesses are the same here, what kind of specimens are really used, but if we calculate it, then we can see that the theoretically calculated residual stresses are close to the experimental ones. So the model works quite well to predict the residual stresses. And with this, we are at different design examples. You already know this from the satellite reflector from the beginning. This is similar to the one we have seen in the video. But we can also have not rectangular, but arbitrary shapes cut it down. And here you can also see that these actuators, if they are thin, are really bendable and do not break. So coming to the last topic of this lecture, tensile tests on D31 piezocomposites, or functional modules. We have a setup shown here, functional modules with applied tabs and strain gauges on it. So we can measure the strain applied to the specimen with strain gauges, but can also get a signal from the piezoceramic, from the functional module. And we there were 3 different tests performed, a loading between 0 and 200 Newton to get the Young's modulus and also the Poisson's ratio. Then we had a loading from 0 to 500 Newton to measure the free strain. We won't have a look at these results, just at these results, and also at the loading to failure to get the tensile strength and the elongation at break. And the results were that there is an influence of the film on the elastic behavior with an open circuit electrodes. The charges cannot discharge, so they cannot flow. And this causes an active stiffening of the module. So if we don't connect the electrodes to each other, the Young's modulus is higher. Open electrodes leads to a Young's modulus of 22.3 gigapascals. And if we shortcut them, then we don't have this active stiffening effect of 19. So we only had a Young's modulus of 19 gigapascals. And also the Poisson's ratio, so the transverse contraction is affected. Here's a force displacement or force strain, force strain plot with open electrodes, so short-cutted circuits and with closed circuit. And here you can see the stiffer behavior of the ones with the open electrodes and less stiffness with the closed electrodes. And when we load it to fracture, again, a force strain diagram with microstrains here, then we can see that in green there's the signal from the strain gauges going up this way, and we have a similar signal from the piezos, but with a curvature the other way around. And here at this point we have a failure there, the strain gauges disconnect, so we don't have a reading anymore, and also the piezo breaks, so we don't have a reasonable signal, at least from this point on. Young's modulus we had on the slide before, short and open, but also the force to fracture was only measured with short-cutted electrodes, which is about 639 newtons. And with this, we come to the summary of this lecture. We can have different semi-finished products for piezoceramics: plates, foils, fibers, or stacks. They are manufactured in a similar chain, but with different processes. We have first the powder, we form it, then we have the sintering and the polarization. We combine the piezoceramic with polymers to form the piezocomposite. And with this, we increase the fracture toughness and the reliability. And we can also easily include electrical insulation, also robust contacting, so these 2 points where we can solder our wires. We learned a bit about connectivity. So different connectivities form different composites from piezoceramics and polymers. Then we had a look at the functional modules, especially D31 film and D33 fiber actuators, so planar actuators, but also stack and multi-layer actuators. And we had a look at the manufacturing process, which leads to residual stresses, which is beneficial because then we can secure the brittle piezoceramic a bit due to the due to the compressive residual stresses in the ceramic, and therefore we have a more robust system. And with this, I'm at the end and open for questions. Do you have questions? Okay, not at the moment. Then we will have the tea break, and afterwards look at actuators.